Hello, everyone. Thank you for watching my presentation. I'm glad to have the opportunity to participate in this special virtual conference, Cosmology from Home 2022. I'm Daneng Yang, currently a postdoc affiliated to the University of California, Riverside. In my talk today, I'm going to introduce you some of our recent works in collaboration with Haibo Yu, also from UCR, on the structure of dark matter halos with differential elastic scattering cross-sections. The main character of my talk today will be dark matter halos, which originates from cosmic structure formation. In the standard cosmology, structure formation may be pictured by three main aspects. At large scales, cold dark matter particles collapse under their self-gravity into gravitationally bound objects. These objects will grow their mass through merger process with tidal interactions, and eventually today at small scales, dark matter particles will re-establish pressure equilibrium and could be self-interacting. Actually, the self-interacting dark matter, that is SIDM for short, has been a well-known scenario that has been introduced to address a number of observational problems. The most known ones includes the diversity problem, where at a constant Vmax value, the observed circular velocity at a fixed radius has a dramatically large spread comparing to this cold dark matter simulation counterpart. The second is core-cast problem, where it is observed that in some halos, the inner density profile are shown to be cored instead of Caspi as predicted in cold dark matter scenario. The too big to fail problem, where in cosmological cold dark matter simulation, some of the most massive subhalos are found to be missing their luminous counterparts. So in this talk, I'm going to focus on the relation between particle level dark matter scatterings and the structure of dark matter halos. I will begin with an introduction of some dynamic properties of dark matter halos, and I will show you how to quantify the correlation between SIDM and the halo structure. During this discussion, I'll show you that some halo level characteristics can be naturally introduced, and these characteristics can be included as weights in a network of dark matter halos. Let me start with some dynamical properties of the dark matter halos. As you know that a thermalized system has a temperature and a Maxwellian velocity distribution. However, a halo of finite mass cannot be a thermalized system. On the other hand, if dark matter self-interaction is considered, these scatterings will drive the velocity distribution to a Maxwellian function. For example, the figure shown here is an example where the velocity distribution in red is fitted with Maxwellian form in the black, where you can see the agreement is almost perfect. As a result, an SIDM halo will demonstrate thermodynamic properties, and the temperature of a halo will be a function of radius. So to formulate a thermodynamic description for a halo, we start from the Boltzmann equation for the distribution function, where we include the SIDM effect in a collision term over here. And we use the unbody technique to effectively solve this equation, where we simulate dark matter self-interaction considering fully differential cross-sections, including a molar and a Rutherford-like scattering, where the cross-section is both angular and velocity dependent. By taking moments of the Boltzmann equation, you will see that one can obtain the equation for pressure equilibrium, and by taking the second moment, one obtain the transport equation for the heat and energy flows. So in this slide, let me show you that by reconstructing two sides of the pressure equilibrium equation and the energy transport equation, we are able to use unbody to directly check both sides of these equations. These agreements really confirms that in a halo, in an SIDM halo, one can use thermodynamics to describe its evolution. So more specifically, we show that a temperature can be introduced to a halo system, where we define the temperature as m times sigma squared. I collect also some equations here to show you that we can, based from unbody simulated particles, we can reconstruct entropy, heat capacity, and luminosity based on the density and velocity dispersion profiles. In this slide, I show you the reconstructed luminosity and heat capacity from our unbody simulations. Interestingly, from these reconstructed luminosity and heat capacity profiles, we are able to arrive at a thermodynamic explanation for the stages of gravothermal evolution. At early times, where a negative heat flux plus a positive heat capacity leads to a core formation. In the intermediate times, about 10 gig a year, a positive heat flux plus a positive heat capacity leads to a relatively stable core, while at late times, a positive heat flux plus a negative heat capacity leads to a core collapse in the inner density. So in our embodied simulation, we have simulated both constant cross-section and differential cross-section. And observationally, we'll be interested in how this particle level scattering cross-section correlates to the halo structure, which affects more directly to the observables. And by quantifying this, we will really be able to extract particle level information, which I'll show you. So let's first realize that the most important gradient in the thermodynamics of a halo is the energy transport. However, this energy transport is complicated by the inclusion of potential energy and by the long mean free path of particle collisions. If we look at the based on the thermodynamic quantities we reconstructed from embodied simulation, we can directly estimate the thermal conductivity, which evaluates to a number 10 to the 5th power over here. However, in conducting fluid models, actually people use the thermal conductivity equation directly computed using kinetic theory, assuming atomic gas. And based on that equation, one finds that the number is 10 to the 9th, which is 4 orders of magnitude higher than the one estimated from our embodied simulation. So what is the problem? Actually, this can be intuitively understood because when the mean free path of particle scatterings are much longer than scale radius of the halo, after considering post-scattering particles, they evolve under gravity and orbit around the halo for multiple times. Effectively, the heat conduction caused by the scattering will be diluted by a number of times as it orbits around the halo. So that causes a strong suppression in the effective energy transport. However, interestingly, we note that in our embodied simulation, there is actually no need for such a long mean free path thermal conductivity. The reason is that the post-scattering evolution is completely governed by gravity and has nothing to do with particle scattering. So motivated by that, we think that the weighting kernel of the kinetic theory thermal conductivity can actually be exploited to average out the differential cross-section such that the simulation can be approximated by a non-differential cross-section. Motivated by this, we propose a so-called conductivity cross-section as shown in this equation, where the integration kernel is sine theta squared with a velocity v to the 5th power, and it couples to a differential cross-section. To show what is to gain a feeling about this equation, we compare this conductivity cross-section to a more familiar thermal average of the cross-section. As you can see in the figure, our conductivity cross-section corresponds to the pink curve. However, the sigma v thermal average value corresponds to the brown dashed curve. From our embodied simulation, we found that the simulation result can be well approximated by a constant isotropic cross-section, 10 centimeters square per gram. As you can see, it agrees with our conductivity cross-section, but the thermal average value is at least 1 order of magnitude higher. So interestingly, the simulation result supports our conductivity cross-section, and the interesting physics with this conductivity cross-section is that its integration kernel couples to the halo velocity dispersion. All right, so as you have seen that our conductivity cross-section is radius dependent. However, to better address observational problems, we'll be interested in remove this radius dependent and obtain a constant cross-section for application. And this naturally leads to a characteristic quantity for the SIDM study. So in this slide, I show you again the conductivity cross-section at different times, and on the right, the evolution of inner density inner density of our benchmark halos. As you can see, the SIDM 10, where 10 means 10 centimeters square per gram for a constant cross-section, and SIDM 10 approximate very well the differential cross-section, where we have introduced characteristic velocity dispersion to remove the radius dependency in the conductivity cross-section. And from the left figure, you may notice that in the inner region, as time goes on, the conductivity cross-section quickly decreases, and meaning that effectively the scattering is much lower than SIDM 10. This result make us wonder that if SIDM effect at late times is actually more effective at large radius around 0.5 kpc. So kind of surprisingly, the answer is yes. From our n-body simulation, we show that if we exclude particle scatterings at radius greater than 0.5 kpc, there will be no core collapse. And if at a later stage at 10 gig year, we turn on the scatterings again, the core collapse will continue. So we show that SIDM at large radii really plays a crucial role in core collapse. Here is our constant effective cross-section. And during this study, we learned some interesting features. First of all, the details of particle dynamics are hidden in a single halo. Next, only the velocity dependence coupled to the halo velocity dispersion, a characteristic velocity scale can be used to capture the majority of the correlation, and only at the late times, the core collapse, there will be a deviation. So to address, we have been talking about a single halo. To address observation, we need to study a population of halos. Here is a cartoon to show how this can be achieved. We have 3 halos of different sizes, assuming 3 different particle physics models, model 0, which predicts SIDM 1, 1, 1 for all the 3 halos. However, in another model, for example, model 2, it predicts SIDM 100 for halo 1, but SIDM 0.01 for halo 3. That is the generic idea showing that how this degeneracy in particle physics models can be predicted by considering a number of halos. And more interestingly, these halo level characteristics can be assigned to nodes in a graph in the learning graph neural network studies. Motivated by that, we arrive at a relevant study which shows that the clustering of dark matter halos can be described in a network of dark matter halos. Let me show you 2 examples based on one cosmological zooming simulation. If considering n equal 40, a number of 40 subhalos in a main halo, and we create a link of a subhalo to its least massive host halo, we will actually arrive at a connected graph for a main halo system. On the lower left, I show you the same graph, but increase the number of halos to 600. As you can see, from the clustering of these nodes, we can tell where the Milky Way host is and where the LMC is. So it really carries physical information. In our work, we actually constructed a random graph model that exploits preferential attachment mechanism to reproduce almost all the features from the simulated graphs. Our model effectively incorporates the effects of major merger, minor merger, and tidal stripping. And our study really provides a new example of scale-free network. Speaking about application, there are 2 possible kind of applications. One is directly topological data analysis. The other is graph neural network, where, as I just mentioned, halo level characteristics can be encoded into weights of nodes and links, and I can exploit graph neural network study to extract SIDM, for example, SIDM characteristics. This kind of practice have been applied to study already halo shapes, orientations in very recently. So as a brief summary, SIDM really leads to novel gravothermal evolution of a halo, and the effect of differential cross-section is largely degenerate to a constant cross-section in a single halo. If we consider a population of these halos, we'll be able to predict the degeneracy in particle physics models, and it's promising to apply graph-based techniques to explore small-scale physics. That's all my talk. Thanks for your attention.